So, good morning, Arun. So, in the previous class, we discussed about introduction to propositional calculus. Next one, well-formed formula in propositional calculus, truth tables, equivalence laws, propositional logic, and another one, natural deduction system. Right. So now let us start about natural deduction system today. There's NDS, natural deduction system, right? So in this particular natural deduction system, we have. So let us see some of the rules and symbols, and based on those rules, how to solve a given problem, right? Let us discuss about this. Coming to NDS, natural deduction system. So let us see this one. Okay. So in NDS. So let us see some of the rules here. Introducing and. So we can represent it as I colon and. Okay. Next, the rule here is if A1, A2, and so on up to AN, then A1 and A2 and so on up to AN. So description about this rule is if A1, A2, and so on up to AN are true, then their conjunction, that is A1 and A2 and A3 and so on up to AN, is also true. If this is true, then conjunction is also true. Okay. Just coming to the rule number 2, eliminating and. We can represent it as E colon and. So the rule here is if A1 and A2 and so on up to AN, then AI 1 less than or equals to I less than or equals to N. Okay. So description about this rule is if A1 and A2 and A3 and so on up to AN is true, if all these are true, then any AI is also true. Then any AI is also true, right? Next, coming to next one, next rule, introducing V or introducing R, introducing R. So that we can represent it as I colon R. So rule is if any AI 1 less than or equals to I less than or equals to N, then A1 or A2 and so on up to AN. So description here is if any AI that is 1 less than or equals to I less than or equals to N is true. If any AI, then A1 or A2 or A3 and so on up to AN is also true. Next one, eliminating or, E colon or. So here is if A1 or A2 or so on AN, A1 implies A, comma, A2 implies A, and so on up to AN implies A, then A. So description here is if A1 or A2 or A3 and so on up to AN, A1 implies A, A2 implies A, A3 implies A, and so on up to AN implies A are true, then A is true. If this is true, okay, then A is true. Like next one. Introducing implies. So I colon implies. So if from alpha 1 comma alpha 2 alpha 3 and so on up to alpha n infer beta, if alpha infer beta is proved, then alpha 1 and alpha 2 and alpha 3 and so on up to alpha n implies B is proved. If this is proved, this is proved. Right? If given that alpha 1 alpha 2 alpha 3 and so on up to alpha n are true, and from these we deduce beta, then alpha 1 and alpha 2 and alpha 3 and so on up to alpha n implies beta is also now let us see some other rules. Eliminating implies. Eliminating implies. Eliminating implies. So E1 colon implies. If A1 implies A, if A1 implies A, comma A1, then A. If this implies this, then A. Okay, description here is if A1 implies A and A1 are true. If both of these are true, then A is also true. So this particular rule is known as modus ponens rule, MP rule. Okay. If this is true, then this is true. Okay. Next. Next one, introducing equivalence. So this particular WR is equivalence symbol. Introducing equivalence. I colon equivalence. If A1 implies A2, A2 implies A1, A1 implies A2, A2 implies A1, then A1 equivalent to A2. Okay. So description here is if A1 implies A2 and A2 implies A1 are true. If both of these are true, then A1 is equivalent to A2 is also true. Next, eliminating equivalence. Eliminating equivalence. So E colon implies E colon equivalence. If A1 equivalent to A2, then A1 implies A2, comma A2 implies A1. Next, if A1 implies if A1 equivalent to A2 is true, then A1 tends to A2 and A2 tends to A1 are true. If this is true, this is true. Next, introducing negation. Introducing negation. So I colon negation. If from A infer A1 and not A1 is proved, then negation A is proved. Okay. If from A infer A1 and negation A1 then is proved, then negation A is proved. If from A which is true, if from A which is true, the contradiction is proved. Contradiction means negation. Okay. Contradiction is proved, then truth of negation A is also proved. If this is proved, then this is proved. Next, eliminating negation. E colon negation. If from negation A infer A1 and negation A1 is proved, then A is proved. If from negation A, the contradiction is proved, then truth of A is also proved. If the contradiction is proved, then truth is also proved. Next one is natural deduction. Next, now let us see some examples regarding NDS. So the question given to us is prove that A and B or C is deduced from A and B. So we have to prove that A and B or C is deduced from A and B. Okay. So the theorem in NDS can be written as from A and B infer A and B or C in NDS. A and B infer A and B or C in NDS. Now let's see how to prove the problem or how to prove the theorem. So I have to write three things here. One is description, formula, and comments. Okay. So description here is theorem. I have to prove the theorem, right? So the theorem is to be written here. So from A and B, infer A and B or C. So I have to write like this in NDS. From A and B, infer A and B or C. So comments is to be proved. So this is the theorem that is to be proved. Now at the hypothesis. Now at the given hypothesis. So what is given to us is A and B. A and B. Okay. Next, A and B is given to us. We need to prove it is equivalent. It is inferred from A and B or C. Now, so next one, A and B. Next, that is first step. Next one. Here I have applied and here. Okay. Now let us see. That means by introduction or by elimination, we need to prove the theorem, right? So E colon and of 1. E colon and of 1. This one. That is second one. E colon and of 1. Okay. So E colon and of 1. So if I write like that, I'm going to get the last one, that is A. Okay. So E colon and of 1 means I'm going to get and here. Going to get and here. Okay. Next, E colon and of 1. E colon and of 1. That means by applying this particular eliminating and, so by eliminating and, what I need to get here. So E colon A of 1 means and is to be eliminated. If I eliminate and, I'm going to get the first one, that is A. Next, E colon and of 1. Okay, already A is eliminated. So the remaining there is B there. So I will get B. So I got A and I got B. Next. Now, after getting A and B, next one, I need to get B or C. In order to get B or C, what I need to apply? So introducing R of 3. Introducing R of 3. Introducing R means this one, the third one. Introducing R. Introducing R. So then I'm going to get B or C. Then I'm going to get B or C. Okay. Now I got B or C, right? Now I need to get, so that means by applying which thing I'm going to get A, and that means I need to introduce and there. So I have introduced this I colon and of 2 comma 4. I colon and of 2 comma 4. That means, so then I'm going to get, if I introduce I colon and, then I'm going to get A and B or C. So the theorem is proved. So this is how to prove the given theorem. Next one. Now another example. Prove the theorem. Infer A implies B and B implies C implies A implies C. That is the problem given to us. Now the theorem infer A tends to B and A. So A tends to B and B tends to C implies A tends to C. Okay. Now the theorem infer A tends to B and B tends to C implies A tends to C is reduced to the theorem from A tends to B, B tends to C, A tends to B, B tends to C, then A tends to C using reduction theorem. So we need to reduce to the theorem from okay. So you need to infer A tends to C using the reduction theorem. So for that to prove that A tends to C, so we will have to prove a sub theorem from A infer C. So the proof of the theorem is like this. First theorem is from A tends to B, comma B tends to C. Now let us see how to solve the problem. So theorem here is from A tends to B, B tends to C, infer A tends to C. So to be proved. Next hypothesis 1 is A tends to B. Next hypothesis 2 is B tends to C. Okay, so first hypothesis is A tends to B. Second hypothesis is B tends to C. Now sub theorem is from A infer C. From A infer C. This is sub theorem. From A infer C. Next, so now next the hypothesis here is A. Next, so in order to get at last I need to get E tends to C, right? So so eliminate, that is E implies 1 comma 3.1. So 1 comma 3.1 means 1 comma 3.1. Okay. So A implies B. A implies B. So you want to get B. Next, E colon implies E colon implies 2 comma 3.2. So 2 comma 3.2 means 2 comma 3.2 means I'm going to get C. So I got A, B, and C. Okay. Next, now I need to get A tends to C. So A tends to C means implies 3. That means from A infer C. That means I will get A tends to C. So like that, I'm going to prove the theorems. Right? Okay. Next one is next type of system is axiomatic system. Axiomatic system. So this particular axiomatic system is based on a set of 3 axioms and one rule called modus ponens rule, MP rule. Okay. Although it is minimal in structure, it is as powerful as truth table and NDS. So to see it is minimal in structure. That means it seems to be a okay. So So, uh, so although it is minimal in structure, it is as powerful as truth table and NDS. Next, in this system, only two logical operators will be there. Only two logical operators, that is not and implies. Not and implies. The so not and implies are allowed to form a formula. So here it should be noted that other logical operators like and or equivalence, all these can be easily expressed in terms of not and implies. So by using these two, that is two symbols like not and implies, I can easily express all the and or equivalence, all these. Okay. So for example, A and B. So A and B is given to us. So that is equivalent to negation of negation A or negation B. That is equal to negation of A tends to negation B. Negation of A tends to negation B. Next, if A or B is given to us, it is equivalent to negation A implies B. Next, A equivalent to B. It is equivalent to A tends to B and B tends to A. That is equivalent to negation of A tends to B tends to negation of B tends to A. So in axiomatic system, alpha, beta, gamma, all these are well-formed formulas. In axiomatic system, alpha, beta, and gamma are well-formed formulas. Here axiom 1 is alpha tends to beta tends to alpha. And axiom 2 is alpha tends to beta tends to gamma tends to alpha tends to beta tends to alpha tends to gamma. Next axiom 3 is negation alpha tends to negation beta tends to beta tends to alpha. Okay. Now next modus ponens rule, MP rule. Here the hypothesis is alpha tends to beta and alpha consequent beta. Next, interpretation of modus ponens rule. Given that alpha tends to beta and alpha are hypothesis, that is assumed to be true, beta is inferred true as a consequent. Okay. Now let us see how. Now let's see axiomatic system. Now let's see how to solve a particular problem using an axiomatic system. So establish that A tends to C is a direct consequence of A tends to B, comma B tends to C. That is A tends to B, B tends to C. Okay. Next, now the theorem given to us is A tends to B, comma B tends to C, tends to A tends to C. I need to prove this one. So hypothesis 1 is A tends to B. Hypothesis 2 is B tends to C. So with these two, I need to get A tends to C, right? That is at last I need to get A tends to C. Next, so instance of axiom 1 is B tends to C implies A tends to B tends to C. Next, modus ponens rule is to be applied on 2 and 3. Then I am going to get these two will be crossed there, and I will get A tends to B tends to C. Next, instance of axiom 2 is A tends to B tends to C means implies A tends to B implies A tends to C. So that is axiom 2 instance. Next, modus ponens on 4, 5. That means A tends to B tends to C, and this fifth one. So by applying these two, those two will be crossed over there. Then I will get A tends to B implies A tends to C. Next, now apply modus ponens on 1 and 6. 1 and 6 means A tends to B and this one. Now I am to get A tends to C. Like that. I will get the required answer, right? Next, Next one, prove negation A tends to B by using deduction theorem. If we can prove negation tends to A tends to B, then using deduction theorem, we have proved negation A tends to B. Now let us consider the theorem. Negation tends to A tends to B. That is to be proved. Next hypothesis 1 is negation A. Next instance of axiom 1 is negation A tends to negation B tends to negation A. Okay, that is the first, and that is the second one. Next, apply modus ponens on 1 and 2. Then I will get negation B implies negation A. Next, instance of axiom 3. That is negation B implies negation A implies A tends to B. Okay. Now apply modus ponens on 3 and 4. Then I'm going to get A tends to B. Okay. Next one. Next topic is semantic Tableau system. Semantic Tableau system in propositional logic. So in both of these NDS and axiomatic systems, forward chaining approach is used for constructing proofs and derivations. That means forward chaining approach means from start state, you will go to goal state. Start state to goal state. Backward chaining means from goal state, you're going to get start state. Forward to backward means start state to goal state means forward chaining. Next, goal state to start state means backward chaining. Okay. Next, so here in NDS and axiomatic systems, we're going to use forward chaining approach to construct the proofs and derivations. So in this approach, we start proofs or derivations from a set of given set of hypotheses or axioms. So we're given a set of hypotheses and or axioms. From these, we're going to start the proofs or derivations. Okay. So in this particular semantic Tableau system, proofs follow for backward chaining approach. Backward chaining approach means last to first. That means from goal state you're going to from goal state you are going to go to start state. Goal state to start state. That is backward chaining. Okay. So in this particular semantic Tableau system, a set of rules are applied systematically on a formula or a set of formula in order to establish consistency or inconsistency. Okay. Now let us see some of the rules in semantic Tableau rules. So the semantic Tableau rules are given below, where alpha and beta are two formulas. Here alpha and beta are two formulas. Rule 1 is a tableau for a formula alpha and beta is constructed by adding both alpha and beta to the same path or same branch. Alpha and beta is true if both alpha and beta are true. So I'm going to represent this like this. Alpha and beta tends to alpha tends to beta. If alpha and beta is true, then both alpha and beta are also true. If both alpha and beta are true, then we're going to get alpha and beta. That means from backward chaining is nothing but you need to get alpha and beta. So we need to get alpha and beta. So that is the goal state. So goal state is alpha and beta here. Now we're going to go to start state, that is alpha beta. If this is true, then this is true, like that. Next, rule number 2 is a tableau for a formula negation of alpha and beta is constructed by adding two new paths. A tableau for a formula negation of alpha and beta. Negation of alpha and beta is constructed by adding two new paths. One containing negation of alpha and other containing negation of beta. Now it can be represented like this. Negation of A and B is true if either negation alpha or negation beta is true. If this is true, then this is true, right? We can represent like this. Negation of alpha and beta, negation alpha, negation beta. Next, rule number 3. A tableau for a formula alpha or beta. A tableau for a formula alpha or beta is constructed by adding two new paths, one containing alpha and another containing beta. Alpha or beta is true if either alpha or beta is true. I can represent like this. Alpha or beta, alpha, beta. Next one. So rule number 4 is a tableau for a formula negation of alpha or beta is constructed by adding both negation of alpha and negation of beta to the same path. So I can write like this. Negation of alpha or beta is true if both negation alpha and negation beta are true. So representation is like this. Negation of alpha or beta, negation of alpha, negation of beta. Next. A tableau for negation of negation alpha is constructed by adding alpha on the same path. That is, negation of alpha is true, then alpha is true. Okay. Next, rule number 6 is rule number 6. A tableau for a formula alpha tends to beta is constructed by adding two new paths, one containing negation of alpha and the other containing beta. Alpha tends to beta is true, then negation alpha or beta is true. So a tableau for a formula negation of alpha tends to beta is constructed by adding both alpha and negation beta to the same path. That is, negation of alpha tends to beta is true, then alpha and negation beta is true. Negation of alpha tends to beta, alpha, negation beta. Like that you're going to get. Next, rule number 8 is a tableau for a formula alpha is equivalent to beta is constructed by adding two new paths, one containing alpha and beta and another containing negation alpha and negation beta. Which are further expanded. So I need to write like this: alpha equivalent to beta is true, then alpha and beta or negation alpha and negation beta is true. I can write like this. Right? Alpha double implies beta, alpha and beta, negation alpha and negation beta. Okay, next rule number 9 is a tableau for a formula negation of alpha equivalent to beta is constructed by adding two new paths, one containing alpha and negation beta and the other containing negation alpha and beta, which are further expanded. So I can write like this: negation of alpha equivalent to beta is true, then alpha and negation beta or negation alpha and beta is true. Okay. So I can write like this: negation of alpha equivalent to beta. So alpha and negation beta, negation alpha and beta. Next one. Now let us see an example here. Construct a semantic tableau for a formula A and negation B, and negation B implies C. Okay, now see this one. A and negation B, and negation B implies C. A and negation B, and negation B implies C. So that is line number 1. Next, now apply rule number 1. Okay, rule number this one, rule number 1. So by applying rule number 1 on 1, I'm going to get A and negation B. Next. Okay, next. Rule number next one. Once again, apply rule number 1 on second line. So then I'm going to get so negation B tends to C, A, next negation B, right? Okay, next one. Right. Okay. Next, if I apply rule number 6 on 3, then I'm going to get um, negation B. So I'm going to get the negation of negation B and C. Then I'm going to get B here. And rule number, by applying rule number 3 on 6, I'm going to B negation. Okay, right? Next topic, predicate logic. So next topic is predicate logic. So logic is nothing but here we're going to consider the truth of statements. Truth, whether it is true or not. We're going to concern here about the truth of statements. Logic is concerned with the truth of statements about the world. Generally, each statement is either true or false. That means either true, going to get either true or false values. Logic includes syntax, semantics, inference procedure. All this come under logic. So coming to syntax, syntax means it specifies the symbols in the language about how they can be combined to form sentences. That means by combining the words, we're going to get the sentences. So you need to specify those sentences in the form of symbols in a language. Next, the facts about the world are represented as sentences in logic. The fact, we're going to represent the uh, we're going to represent the facts in the form of sentences. So we're going to represent the we're going to represent the sentences in logic, which are facts. Facts are going to be represented in as sentences in logic. Next, semantics. Semantics is nothing but giving meaning to a value. So if something has a meaning, then that is nothing but semantics. It specifies how to assign a truth value to a sentence based on its meaning in the world. So based on the meaning, we're going to assign the truth value to a sentence. Next, it specifies what facts a sentence represents. Specifies what facts sentence represents. A fact is a claim of the world and it may be false. Fact is nothing, it may be either a true value or false. Next one is inference procedure. So this particular inference procedure specifies the methods for computing new sentences from an existing ones. Based on the existing ones, we're going to refer to we're going to compute sentences. Right? There is nothing but inference procedure. Next topic is now let us see what predicate logic. Predicate logic is the study of individuals and their properties. It is the study of individuals and their properties. Now let us consider some of the examples here. Here we are given some set of sentences. Marcus was a man. Marcus was a Pompeian. All Pompeians were Romans. Caesar was a ruler. All Romans were either loyal to Caesar or hated him. Everyone is loyal to someone. People only try to assassinate rulers. They are not loyal to. Marcus tried to assassinate Caesar. So these are some of the sentences given to us. Right? Now we need to represent these in the well-formed formulas. Right? Okay. So So we're going to discuss this topic in the next class. Okay, thank you.